Okay, so for our second result in our limit theorem section, we have properties, well, not properties, we have how the limit operates with the normal operations that we do on the reals. So we have addition, subtraction, multiplication, multiplication by constants, and division. With this theorem here, we say that the limit across multiplication distributes. So the limit of the sum is the sum of the limits. Same thing with subtraction. Limit of the difference is the difference of the limits. Limit of the product is the product of the limits. And the limit of a constant times a sequence is just this constant times the limit of the sequence. So we're going to walk through these proofs. So here's the proof of the first part. Proof I. So limit of the sum is the sum of the limits. So we can say, oh, this one, we can say let epsilon be greater than 0 and observe maybe not there, observe that there exists a prime and k double prime, which are just natural numbers, such that if n is greater than or equal to k prime, then xn minus x is less than epsilon over 2. And if n is greater than or equal to k double prime, then the same thing holds for y. All right, so I just kind of did this in a quick manner. I just stated the definition of convergence, right? If the limit of xn is x, the limit of yn is y, then there is some index so that if n is bigger than that index, then the distance from xn to x is at most epsilon over 2. That's some positive number, we can always do that. And then if n is greater than or equal to k prime, then the distance from yn to y is at most epsilon over 2. Okay? So that's just stating the definition of convergence. So then we want to show that we can find an index where that is arbitrarily close to that. So let's look at the magnitude of this. So xn plus yn minus x plus y. We want to get an estimate on how big this is in terms of epsilon. So this is equal to xn minus x and then plus yn minus y. Okay? So then I can use the triangle inequality again. But then we know that this is bounded above by epsilon over 2, and this is bounded above by epsilon over 2 whenever n is greater than or equal to k double prime for that one, and whenever n is greater than or equal to k prime for this one. So I'm going to go ahead and say this. This is strictly less than epsilon over 2 plus epsilon over 2, which is equal to epsilon whenever n is greater than or equal to the sup or the maximum of k prime and k double prime. So if n is bigger than both of these, then both of these inequalities hold. So that's at most that, and that's at most that. So we get our estimate That's bounded above by epsilon for n greater than that. That's whatever index that is, that's one that we would choose to verify that, yes, that gets arbitrarily close to that. The proof of part double I, this is the same argument. So I encourage you to fill in those gaps. Use this same argument to prove this here. Okay. All right, so now I'm going to prove part 3. Okay. So our goal is to show that times that, and then pass the limit to these two sequences to get the product of their limits. So this one's kind of, I guess, algebraically tricky, maybe, but really it's just a standard technique that you just will see over and over again in analysis. Part 3. Okay. When we first consider that if we just look at what this is, right? We want this quantity to be small, right? We want to figure out how to make that quantity small for some choice of an index, right? Some choice of k is what we've been using. So notice that this is equal to, if we just, we have x in, y in, so if we just add, say, there's two choices, I'll do this one. X in y minus x in y, we're adding 0 again, we do this all the time. That's y. I notice we can kind of group these together, right? And then we can, I'll go ahead and write it. Let's see. I can factor out x in from this part here. Where is it? Do I want to do that? Oh, maybe I want to do this. There. The goal basically is to use that and that, right? We know that xn is close to x for large enough index n, yn is close to y for large enough index n. So that's the whole goal. I'm trying to figure out how to do that, and I see that if I make this a negative and that's a positive, then I can kind of do it. So here, if I take out an xn, I get yn minus y. And I know for large enough n, that's small. I'm like on the right track. Plus, if I take out y here, I get xn minus x. So I'm on the right track. I know that that's going to get small and that's going to get small eventually. So, and my goal is to make that small, getting there. So now I can use the triangle inequality. Like that. Oh. There. And now the absolute value of the product is the product of absolute values. So this is actually equal to and then I can already see that this statement is true. Looking at this right here, when we see that that is at most this, why would I believe that to be true? I know that gets small and that gets small, right? That's a start. That's just a number though, right? Y is just a number. So that's some finite thing, right? But then what about this term here? The n can vary off to infinity, right? So how do I know this doesn't grow without bound and somehow I can't capture that, right? Well, by the previous theorem from the previous lecture, we know that xn is convergent, which means that it's bounded. So in absolute value, xn is bounded by some m, right? So I'm going to go ahead and say that. So since xn is convergent, xn is bounded by a previous theorem. Right? If the sequence is bounded, that means in absolute value, it can be no more than some real number m. Hence, we may choose m, some real number, positive real number, so with m greater than 0, such that in magnitude, xn is always bounded above by m for all natural numbers n. So now we're getting close. We know that that's bounded. That's just some real number. And then that's also small and that's small. So now I believe even more so that I can get a good estimate on this difference here. So now I just have to choose it kind of, well, I can say this. I can say let I don't know, Q be the maximum or the supremum of M, and Y. That's just a real number. That's like the limit of the sequence Yn. Okay. So then I'll call this maybe equation star, that's at most this, right? So then I can say then we observe star, that thing, that xn times yn minus x times y, which is at most this, right? Is at most q times yn minus y plus q times xn minus x. Right, because q is the supremum of m in absolute value y, so that's bounded above by q and that's bounded above by q, so this whole quantity is bounded above by that times that plus that times that. Okay? So then, now that we have that, we just have to find an index where this difference is at most epsilon over q. That distance is at most epsilon over q when n is bigger than that index. And then we will get the desired bound on this distance. So then we can just say let epsilon be greater than 0. And observe that there exists say k prime and k double prime that are just some indices or natural numbers such that n greater than or equal to k prime implies that the distance from x n to x is at most epsilon over q. And n greater than or equal to k double prime implies the distance from yn to y is at most epsilon over q. Okay, and I'm running out of room, so I'm going to make this kind of shorter and just say, thus, if n is greater than or equal to the suit of k prime and k double prime, then I'll call this double star. Is at most epsilon. And we're done. Right? Like, if you took n greater than or equal to that and that, then this would hold and that would hold, which would mean like this would be strictly less than q times epsilon over q, and this would be strictly less than q times epsilon over q. The q's would divide out, and you'd have, oh no, epsilon over 2q. The q's would divide out, and you'd have epsilon over 2, epsilon over 2, 2q, 2q. And then they would add up to the epsilon, which would mean that that's at most epsilon, which shows convergence, which means that we've proven that. Okay, so that proves part 3. Now, to prove part 4, it's actually really easy. Any constant times that is equal to the constant times that. Well, for part 4, takes yn equal to, or I'll write it here, yn equal to c to infinity. So if yn is that, then the limit of yn is equal to c. So then yn times xn is equal to the limit of the product of the limits, which proof of 3 implies 4 if you just choose yn to be the constant sequence c. Okay. Again, the name of the game is just getting estimates at each step, right? We know under assumptions that a sequence converges that eventually for some index, the distance from the sequence to its limit is going to be small. And we just make use of that over and over again together, in this case, with the theorem that we proved that convergent sequences are bounded. So again, we know that this is bounded. That's just a number. That gets small, that gets small. our intuition should say that we can, if we work hard enough, we can squeeze that close to that for some value, some choice of n. Okay, so that'll be it for this recording, and then I'm going to record another one in a separate video, another theorem in the section on limit theorems.